Okay. I don't know why it's doing this. Okay, there we go. So I had to put it in airplane mode so that hopefully I don't get any more calls or messages during my lecture. All right, so this is saying when you weigh yourself, you stand on a spring scale and compress a spring, and that the reading of the spring scale is the force of the spring. It's basically the magnitude of the upward force that the spring is exerting. And weight of an object is the reading of whatever that force of spring scale is. So weight is a measurement, and it's the result of weighing an object. And weight is dependent, well, it's measured in newtons, and it's dependent on gravity. Okay, so this is saying that a bathroom scale uses a compressed spring, and so it's the spring is actually pushing up. You know, when you get on the scale, you push down, you compress those springs. So when any spring scale measures an object at rest, the net force is equal to 0. So the upward spring force exactly balances the downward gravitational force. So these two things are actually equal. And weight is defined as the magnitude of the spring force. Those are equal when the object is at rest, which then gives you that it's equal to mass times gravity. Okay? So it's just very important to keep in mind that mass and weight are different, because mass does not change depending on where you are, where weight can change. Weight can change if you go to the moon. Weight can change if you're in an elevator, if you're falling, free fall, even on Earth. So weight can be different based on the situation that you're in. Okay, so let's see. This is saying that an astronaut takes her bathroom scales to the moon, where gravity is 1.6 meters per second squared. On the moon compared to at home on Earth, what is the correct response here? So on the moon, what is the deal? Well, we said that the mass doesn't change. So we know that the mass has to stay the same. And those are these three options. Now on the moon, there is some gravity. So we know that weight is equal to mass times gravity. So could her weight be 0? No. Could her weight be the same? No. Because her weight on Earth is mass times gravity, which would be whatever her mass is. Let's just say 70 kilograms or something, times 9.8 meters per second squared. Whereas her weight on the moon is now, her mass does not change, but the gravitational acceleration on the moon is 1.67. It doesn't say the 7, but meters per second squared. Okay, so her weight is less, and her mass is the same. Okay? All right, so now this is saying that the figure shows that a man is weighing himself in an accelerating elevator. And it says to look at the free body diagram. So remember, you've got this elevator is actually accelerating. So you're no longer at rest. And if it's accelerating upward in a positive direction, then that means that the net force also has to be in a positive, direction. So the spring force in this case is larger than the gravitational force that's pulling down. And it gives you this equation here. Okay. And you can use this equation to actually figure up like what the weight could be depending on the situation. Depending on if they're accelerating up or if they're going down. So I'm not sure if this is an example in the book or if it was just something like that was written in the text. I'm going to go ahead and stop this video and pull that up. I'm sorry, I have to stop this so many times, guys. I can't have very long videos. You'll find that they'll add up to probably less of what we would have in actual class this week, you know, if I was face-to-face. So it's just sort of a pain to have to stop and start again, but that's kind of what we have to do.